All right, today we're diving into Chapter 7 of Shepli L. Ross's classic text to explore a really powerful idea in mathematics, systems of linear differential equations. Now, I know that sounds intense, but this isn't just abstract theory. This is the actual language that describes how our world is all interconnected. Let's get into it.
So here's a fun one for you. What on earth could the number of foxes and rabbits in a forest have in common with electricity zipping through a circuit? Well, the answer is pretty cool. They are both systems. The change in one part is directly connected to what's happening in another. And to really understand that complex dance, a single equation just won't do the trick.
You know, a single differential equation is great. It's perfect for describing one thing changing all by itself. But in the real world, things are rarely that simple, right? Nothing really exists in a vacuum. The number of predators totally depends on the number of prey, and the other way around. The current in one part of a circuit absolutely affects the current in the next. To model this interconnected reality, we've got to level up from single equations to systems of equations.
So how in the world do we solve these tangled webs of equations? Well, the first tool we get from Chapter 7 is something called the operator method. The best way to think about this is as a really clever algebraic shortcut. It lets us kind of untangle the system and solve for one piece at a time. It's an elegant and surprisingly powerful technique, especially for simpler setups.
The secret sauce to this whole method is the differential operator, which we just call D for short. All we're doing is defining D as the act of taking a derivative. And by doing that, we can magically turn our complicated differential equations into something that looks and behaves just like a regular old polynomial from algebra class. It's this simple but brilliant trick that makes the whole thing work.
And here's the game plan. First, we just rewrite our system using that nifty D operator. Then, and this is the really cool part, we use the exact same algebra tricks we learned in high school to eliminate one of the variables. That leaves us with just a single, much easier differential equation to solve. Once we've got that answer, we just plug it back into the original system to find the other variable. See? It's a beautifully logical process.
Okay, so that's the how, but what about the why? Where does this stuff actually show up? Let's take a look at a classic example that really shows off how useful this is.
So picture this. Two big connected tanks of salt water. You've got fresh water flowing into one, the mixture is getting pumped between them, and the final solution is flowing out. The amount of salt in tank 1 affects tank 2, right? But then the mixture from tank 2 gets pumped back and affects tank 1. It's a perfect feedback loop. This is a real-world system that could be described perfectly by two linear differential equations just waiting to be solved with our operator method.
The operator method is fantastic, but what happens when you have 3 tanks, or 4, or 100 different variables all interacting? That's when we need to bring out the big guns. So let's move on to the second major technique from the chapter, which is way more powerful and scalable, the matrix method.
So here's a standard system, just like one we'd solve with the operator method. We have two equations, two unknown functions, x and y, and you can see the rates of change are all tangled up together. It's clear enough, but you can imagine how cluttered this could get if we added just one more variable.
Now look at this. This is the exact same system, but it's captured in one incredibly clean and elegant equation. All of that complexity from the last slide, it's now packed neatly inside that matrix A. And this isn't just about looking tidy. This unlocks a whole new, powerful way of solving the problem, using ideas from linear algebra, like eigenvalues and eigenvectors. You can think of those as the secret underlying directions that the system naturally wants to move in. It gives us a much deeper insight into what's really going on.
So, we have two solid methods on the table. The algebraic operator method and the matrix method. Which one should you use? Well, like with any good toolkit, it really depends on the job you're trying to do.
This table lays it all out perfectly. The operator method, it's your best friend for simple 2x2 systems. It approaches algebraic elimination, which is pretty intuitive. But its weakness is that it doesn't scale well. The matrix method, on the other hand, is built for the big, complex stuff. It uses the heavy machinery of linear algebra, those eigenvalues and eigenvalues we mentioned, and its greatest strength is that it's highly scalable. You can use the same fundamental process for a 2x2 system or a 100x100 system.
Okay, so let's zoom out. What's the big takeaway from all this? What we've really been learning here is the mathematical language of interconnectedness. We've seen that the world isn't just a collection of random events, but a massive, intricate network of interacting systems.
So if you remember anything, remember these key points. Systems of differential equations are how we model interconnected change. For the simple stuff, the operator method is a quick and clever tool. For anything more complex, matrices give us a powerful and scalable solution.
And this isn't just for physics problems. This is the math that describes everything from chemical reactions and ecosystems to the stock market.
So I'll leave you with this final thought. The next time you look at the world around you, try to see the hidden connections, the push and pull between different forces, the feedback loops, the whole complex dance. What are the unseen systems that are shaping your world right now?